Welcome to Fun with Science, Engineering, and Technology. I'm Mr. Ross, and today what we're going to discuss is force, motion, and mass. All right, my assistants are
Carlos Rivera.
And Julio Contreras.
okay. So it's the beginning of spring training. So what we're going to do is we're going to use a bunch of balls. This happens to be a what?
Softball.
Softball. Right. So if we were to give this to a real professional ball player, and they were to wind up and pitch it, right? And we're going to pitch it like a baseball overhand. What's going to happen to it?
It's gonna go.
It's going to go.
Spin,
But it's all right. I'm down in Fenway, and I wind up and I throw this thing. And tell me what happens.
It's gonna go to the catcher.
Hell no, it's not gonna go to the catcher.
I'm going to stand at home plate. I'm going to throw it out into the outfield. What's going to happen to this ball?
It's gonna go in the air and fall back down.
It's going to go in the air and fall back down. Very good. That's exactly what happens to it. Now, if I were really good and I wind up and I throw it, how fast do you think it'd go?
About 97.
About 97 mile an hour,
Yeah.
25.
right? 95? If I threw it, it'd probably go 25, right?
That's what I said 25.
But if we got a professional ball player that takes this thing and winds up and throws it, it could go almost 100 mile an hour,
Yeah.
right? No. He winds up and he throws it like this. How fast is it going when it leaves his hand?
I don't know.
If he can throw it on 100 mile an hour, right, how fast is it going when it leaves his hand?
It should be going faster than it should when it's when it's in the air.
Should be going faster when it's in the air?
No, it should be faster when he releases it than it should when it's in the air.
Okay, so initially, if we're going to start out with this ball is going to go 100 mile an hour, what I'm doing is I'm sitting here and it's at rest down here. I wind up and I throw it, and what I'm doing is I'm putting force to the ball. I'm causing it to start moving here, right, up over here like this. And when I let go of it, if I'm really good, it's going 100 mile an hour, right? Then what happens to it?
It starts to slow down
It starts to slow down. Why?
because of the force of the gravity.
Because of the force of the gravity,
Yeah, probably.
right? Well, it's going to fall down and hit the ground, because what's going to happen to it is gravity is going to pull it down just like that, right? But why does it slow down?
Because there's nothing pushing it.
Because there's no force pushing it, right? Once I let go of it, all the force that gets this thing going, get it to moving 100 mile an hour, is, well, as long as it's in my hand, I'm putting force to it, right? And I'm causing it to accelerate. It's starting from 0, and it's going up here like this, and it's going to 100 mile an hour. All right, and I let go of it. As soon as I let go of it, the thing that's putting the force to it is my hand and my arm, and as soon as I let go of it, and it starts to move away from my hand, there's no longer any force being applied to it. Right? It's got all the energy and all the force to it that it can have. It's going to continue to go. But when you say it's going to slow down, right? By the time it gets out into the outfield or to the home plate, right? It's going to be going a little bit slower. What causes it to go a little bit slower? Gravity is going to cause it to fall down and hit the ground. But what causes it to slow down?
The mass of the ball.
The mass of the ball causes it to slow down?
Yeah.
What do you say, Julio? You want to make an inference, a guess?
They're gonna throw it too slow.
Got to throw it too slow. Right. What causes it to slow down is the friction.
Oh, with the air in the ball.
Yeah. Right. See, you knew all along. Right. As I throw it, all right, and it starts going through the air. The air is rushing around the ball, and there's a certain amount of friction, which is eventually going to slow it down. So we get it started going, right? When I throw it by putting the force to it with my arm, right, and it starts to travel, right. And as soon as it starts to travel through the air, the friction of the air now is going to cause it to slow down, right? Gravity is going to cause it to go down and hit the ground, right? So no matter how good I am, I'm not good enough to just throw this ball forever and ever and ever down at Fenway Park, right?
If it was in space, it would do that.
What did you say?
If it was in space, it would do that.
It would do what?
Keep on going and going and going.
Why?
Because there's no gravity.
There's no gravity?
But the friction is still there.
Where does friction come from? Friction comes from the air moving around the ball.
There's no air out there.
Oh, really?
So there's no air, and if we go out into outer space, there's no air particles out there to speak of, or not very many, so there's no friction. So then if I took this ball,
Go ahead, keep going.
and I wound up, take a deep breath, and I go to outer space, all right, someplace, and I wind up, and I throw this ball, get it going 100 mile an hour, right?
It'll probably stay 100 miles.
It'll
per hour.
stay 100 mile an hour and just go on forever and ever, right? Because there's no friction. Right? Now, on Earth, down at Fenway Park, pump all the air out, right? We're going to evacuate Fenway Park, take all the air out of it. Called big vacuum. Put Pedro down there, and he's going to throw this ball for me, right? He's going to get it going 100 mile an hour. So it's going to keep traveling 100 mile an hour because we got rid of the air. There's no friction. But what's going to happen to it eventually?
There'd still be gravity. So
It's still going to be gravity. So what's it going to do?
it's gonna fall.
It's still going to fall. Right? So gravity is going to make it fall. Right?
Mhm.
If I were to go to now there's gravity everywhere. Right? Even if I go into outer space, there's going to be things around. Right? There's gravity. Some amount of gravity. There's always going to be a little bit. But I can go to an imaginary outer space. Right? Why do I say that there's gravity everywhere?
Because on Earth, there's an atmosphere.
No, that doesn't have anything to do with atmosphere.
No.
Right? Any two bodies, right? This one and this one. Right? This has some gravity and this has some gravity. I mean, it's attracting. Okay. Now, there's not much here, but there is a little bit. Your head and your head, right, both have gravity, which are attracting. Can you feel the pull, right, between the two heads, right? You're trying to go like this, right?
Oh my God.
As long as you have some material there, right, there's going to be some amount of gravity. So even if I go into outer space, right, and there's a star over here, and there's another planet over here, and there's something else over here, right, there's going to be some gravitational force. It may be very, very weak, right? So I can't really go anywhere in space to a point where I say there's no gravity, right, because there's going to be a little bit. But there may be, we're going to have this imaginary place where I'm going to go. There's no gravity. I take this ball, I wind up, and I throw it 100 mile an hour, and you're telling me because there's no atmosphere, no friction, it's going to keep going at 100 mile an hour. And if we can find that magic place where there's no gravity, guess what? It's going to go in a straight line. It's going to keep going, going, going right in a straight line, right? Now, if it got close to something, like a planet or a star or a black hole, right, which has some gravitational field around
It
it,
starts to like probably slow down.
what's going to happen? It's going
It'll
to
start
be
dropping.
going, well, which way is up?
That's up right there.
That's up there because we're standing on Earth. But if we're in outer space, which way is up?
Nowhere. You don't have.
Okay, keep
All right.
going up.
So what happens if I have over here? All right, I have a big old planet, and my ball's traveling along here at 100 mile an hour. Right, and this planet's gravity. What's going to happen to it?
You're gonna
It's
get
gonna
pulled
go-
over.
It's going to go
there.
over in this direction, right? So if there was no gravity, then it's going to go in a straight line, and it's going to go to a constant speed. Right? Gravity is a force, right, which causes it to go off in some other direction. So what have we done? What have we talked about?
The mass and friction.
We talked about friction. We talked about, right, we take this ball and we throw it, right, and it goes in a straight. If we're out in outer space somewhere where there's no gravity, no friction, right, it's going to continue to go at a constant speed, right, and it's going to go in a straight line. To get it to change its direction, what do we have to do?
Gravity.
We have to have some force, right? If you were standing out there in outer space with your bat, I threw this thing at you, right, and it comes whizzing along at 100 mile an hour, and you hit it with the bat, you're putting a force to it, and you can make it go off in another direction, right? Now, if the ball's traveling like this, and I put a force to it this way, which way is it going to go? I put a force to it this way, which is it going to
It's
go?
gonna go down.
I put a force to it this way, which is it?
Probably go up.
It's
No,
gonna go up.
Go down. Right?
Well, for where we're standing, yeah, it's going to go up, right? It's going to go that way. So it's going to move in the direction that the force is being applied to it, right? Put one in this direction, right? If it's traveling along 100 mile an hour, and I put in this direction, and I put a force to it this way, what's going to happen to it?
It's gonna stop and drop.
It's going. Why would it
Right.
drop?
In outer space, it wouldn't drop, but it'd go the other way.
It would go. It would start slowing down, and then eventually, if we keep the force to it,
Yeah.
it goes and it go in the opposite direction, right? So if we were out in outer space where there's no gravity, right? Now, two balls. I'll let him hold both of them because I'm going to ask him questions about both of them. He's got to have them both. Now, which one's the heaviest?
The softball.
Softball? Right. Which one do you think you could throw the fastest?
The softball.
The softball. Can you make it go the fastest? Do you think so?
Yeah.
You wound up, right? Let's assume now we're in outer space again, right? No air, no gravity. I wound up with this softball, you say, which is the heaviest, and I throw it 100 mile an hour, right? Now I'll take this one, which is lighter, right? And there's no friction or anything, and I wind up with it, put the same force to it. You think it's going to go less speed?
I'd probably go faster in outer space.
It'd probably go faster in outer
Yeah,
space,
it
right?
has
Because
less
there's
weight.
no friction, right? Less weight. It's just like if you get out and you're pushing your bicycle, right? And you can push your bicycle along pretty fast, right? Just because it's not very heavy. But if you take the car, right, and you go out and try to push it,
A little slow
you got to have a lot of more force to push that car, right? Why?
because it's heavier.
Because it's heavier, you say, right? What do you say, Julio? What about a freight train, Julio? We're going to have you push a freight train.
Superman.
You're a free Superman, right? So you're going to push this freight train, right? Can you push it as fast as he's pushing the car?
No,
Why?
because it's heavier than the car.
It's heavier than the car. And is it heavier than the bicycle?
Yeah.
So if I take these three balls then, right, and I've got a softball, I got a tennis ball, and I got this little foam rubber ball, and I'm going out where there's no air, no gravity, right, no friction, and I'm going to throw each one of them with the same amount of force. Which one's going to go the fastest?
The
The
tennis
foam
ball.
ball.
Why?
Because the tennis ball
Is it as heavy as which one's the heaviest?
this one.
Okay, so which one of those two? If you throw them both with the same force, which one's going to go the fastest?
This one.
No.
It was gonna go like that.
No.
No,
outer
let's
space.
do
Oh,
away
outer
with all the
space?
let's do away with all the
No
No
gravity.
gravity, no friction.
No gravity, no
Oh.
friction. Which one's going to go the fastest? On the bicycle, right? If you had a bicycle with no gravity, no friction, and a freight train, and you started pushing them, which one could you push faster?
The bike.
Right.
The bike, right? So why are bikes any different than balls?
Because the ball is round and
Yeah, but it's got what we're talking about.
The
We're
bike
talking
is heavier.
about bike is heavier, right? If you were to pick the bike up and try to throw it, right, you're going to be able to throw it very fast?
Nah.
No, you're not going to be able to throw that very fast. Right? So what we're talking about some mysterious thing here now, right?
we don't know though if anyone will go faster because we haven't been to outer space and thrown a ball.
You haven't tried it, right? Okay. But if you went out and tried it and we were to clock you, we were to get a radar gun and clock you, right? This one, you throw it with the same amount of force. This one's going to go this little, let's say if we throw this on 100 mile an hour, right? We throw this one, which is the next heaviest one, right? It's going to go a little bit slower.
No,
A
faster.
little bit faster, I'm sorry. Yeah, you're right, a little bit faster, right? And then if I throw this one, which is really light,
You can go the fastest.
you're going to go the fastest, right?
Oh, because it don't have no weight. Because it doesn't have no weight.
Because it doesn't have as much weight. It's just like you pushing the bicycle and you pushing the car, right? You can push the bicycle faster than you can push the car because the bicycle
Has less weight.
has less weight, right, than the car. Or it has something called mass, less mass than the car. The bicycle has less mass than the car. This ball has less mass than this ball. So this one's easier to push or throw faster than this one is because this has more mass than this. Now, Got a little ball. What's this thing?
It's a spring scale.
Spring scale. What do we use it for?
Find
To
weight.
measure weight.
To find weight, or this particular one, on one side it's
In grams.
in
Grams.
grams, on the other side it's in newtons, right?
That's less than grams, right?
Right? And every newton is 100 grams, right? And the reason it's labeled that way is because we can also use this to measure force, right? Other than weight. Now, I have a little ball here,
What's
and
spring attached to it?
and I weigh this like this, right? And tell me about that.
50 grams.
It's 50 grams, right? What if we make it, put a little extra weight on it, what happens?
It gets heavier.
It's heavier, right? But what happens up here?
The spring starts to
stretch.
Yeah.
This, okay, so if I take the weight off, right, and it reads, what's it read now? It should read about
Zero.
zero, right? And what's about the spring?
It contracted.
It's contracted, right? Coils are together. I put the weight on it, right? And what happens?
It stretches out.
It stretches out, right? It causes some tension on the string. So what we have then, what's causing this thing to pull down?
The gravity.
Gravity, right? When what's in this spring, it's going to pull down until the spring then pushes up, pulls up with an equal amount of force, right? And that's what gives you the read. If I were to take this and put it on there, what's going to happen to it?
It's gonna go down.
It's going to go down more, right? Because gravity is going to pull this down a little further, and it's going to stretch the spring. So what we actually have was we have two forces here now. We have this force, gravity, which is pulling down, and we have another force. What's causing the other force?
Frictional mass. Or the newtons.
The spring,
Yeah.
right? The spring is what's holding it up, right?
Yeah.
So I've got a force, the spring is pulling it up, gravity's pulling it down, and if I quit shaking, this is going to do what?
It's gonna
Stay
it's gonna
still.
stay there. Right
Stand
there.
still, right? And if I make more weight here, what happens?
The spring starts to like
The
add
string,
more
all
force.
right, I put more force on it here. Once the spring is stretching out and putting more force back up, and if everything is standing still, what about that force pulling up and the force pulling down?
Until
they
they're
are-
both equal.
They're equal, right? So as long as it's standing still, all the forces on it are equal. What about this book?
It weighs the most.
What's it doing?
Nothing.
Nothing is right there.
It's doing nothing? Is there any forces on it?
The gravity holding it down.
Gravity's holding it down,
Yeah.
it's pulling it down, right?
Yeah.
Why doesn't it just fall?
Because of
The table.
Table.
What's
Holding
the
it up.
table doing?
Holding it up.
So if gravity's pulling, let's say this book weighs, say it weighs a pound, right? And gravity's pulling it down on with a force of 1 pound, what's the table have to be doing?
Pushing it up on 1 pound.
Pushing it up with 1 pound, right? How do you know that?
Because it's staying right there.
Because it's standing still, it's not moving, right?
Yeah.
So the forces are all balanced, right? So I got a couple forces that we know about on that book. We've got gravity pulling it down, and we have another force pushing it up, right? Those two forces are what? In opposite directions?
Mhm.
And what else can we say about them?
Opposites attract.
No, that's electricity. They're going in opposite directions, and they are
Meeting on spot.
equal,
Yeah.
right? If they weren't equal, what would happen?
And
That
then go
one-
down.
Or
Right, if
be
this
unbalanced.
table weren't able to push up with a force equal to the weight of the book's going to fall. All right. So, it's sitting there and it's doing nothing, just like we are right now. We're doing nothing, right? We're standing here looking at this book. What happens if I push it?
It moved.
It moved, but then what happened to it?
It stopped
Stand still.
It stopped. Why?
because of the friction.
Because of the friction. Just like
The softball.
the softball down at Fenway, right? I throw it, right? I get it to moving. As soon as my hand lets go of it, right, it starts to do what?
You're
Starts to
slowing
slow
down.
down.
Starts to slow down
It
because
starts
of
to
what?
drop.
Because of
The friction and
Friction.
gravity.
because of the friction of the gravity. Right. So I have my ball again. I have my scale, and if I quit shaking, right, gravity's pulling what?
The ball down.
pulling the ball down, and the spring is
Pulling
Pulling
it
it
up.
up.
pulling up with a force, so there's a force down, there's a force up, and what about those two forces?
They're equal.
They're equal.
They're equal, and they're in opposite directions, right? Forces always come in
Opposite direction.
pairs,
Yeah.
right? We got a force down, we'll have a force up. We have a force sideways, we have a force going this way. They're always in pairs, right? And they're always equal. If I were to take this now, my little spring scale and my little ball, which we said has how many grams?
50.
50 grams, and I go to the moon with it. I hold my breath and I go up to the moon, and I stand on the moon, and I look at it. What do you think it's going to do?
Gonna weigh less.
Weigh what?
Gonna
Way
weigh-
less.
Weigh less. Why?
Because no
because
gravity.
of the gravity.
No gravity?
Yeah.
No gravity.
Moon has no gravity?
Oh
your
yeah, it
your
does.
two heads have gravity. I mean, why doesn't the moon have gravity?
Oh yeah, because it has material.
It has some material, right?
probably
It
gonna
has
pull
some
down.
mass, right? So it's going to have some gravity, right? It's not as massive as the Earth, so it doesn't have as much gravity as the Earth. In fact, it has something approximately 1/6. So if this weighs 50 grams on Earth, right? And the reason we can measure the 50 grams is because the gravity's pulling it down here, the spring is pulling it up, and when it gets to be equal forces, right, we get a scale reading of 50. If I go on to the moon with it now, and this gravity that's pulling it down is what? About 1/6 of the Earth. So what's going to happen to it?
So the scale's gonna be stronger, so it's gonna be on
It's-
equal force.
So the spring is going to be
It's
not up as much, right? And it's going to be way what?
less.
Way less. All right. Now, did I change anything about this ball? It still has the same amount of material and stuff, right? So it must have the same mass, because mass, one of the ways to describe mass is the amount of material. So this thing has the same amount of material, right? So if I took this softball, right, and I went to the moon, here on Earth, if it took so much force to make it go 100 miles an hour, if I go up to the moon, this softball still has the same amount of mass, right? So if I'm going to throw it on the moon and make it go 100 miles an hour, I would have to put the same force to it. Right? What's going to be different about me throwing it on the moon and throwing it at Fenway Park?
Less friction and gravity.
Less friction and less gravity, right? So it's not going to slow down as fast. There is a little bit of atmosphere on the moon, not much, right? Right. So it's going to not slow down as much because there's not as much friction. So it's going to continue going 100 miles an hour for a lot longer. And what about the time it takes for it to hit the ground?
It's be
Longer. It's gonna take
It's
longer.
going to take longer because we only have 1/6 of the gravity. So if I could throw this thing 100 yards down in Fenway, right, on the moon, I could probably throw it 600 yards,
600.
right? 6 times as far. Okay. No. We come to the conclusion a minute ago that, right, the reason we're weighing things here on Earth is because gravity's pulling it down. The spring is stretching a little bit, expanding, and when the two forces are equal, that gives us our reading for how much it weighs. And if we go to the moon, it's going to read about 1/6 the amount. Back in the 6th grade, probably, you used a scale, something like this one. Right? Nice blue scale. Right? And it's a lever, is what it is. It's equal arms on either side, a fulcrum in the middle, a pivot point which it can pivot around. And we got a little mark on this side, which you can't see over there, that shows when it's all balanced up. And what you did is you took a thing like this, put it on one side, right? What happened?
It dropped to that side.
It dropped down.
With
It went down. Why?
because
Because
of
that's
more
heavy.
friction and gravity on that, and because of mass.
Because of the mass, right?
Yeah.
I got more mass on that side than I have on this side. Then what did you do when you want to measure, want to measure something with this thing?
I put
stand
that
on the
quarter
outside.
right there.
right? You had some little weights, right? That you knew well, there we had like 1 gram, 5 gram, 10 grams, and so forth. And you kept adding and subtracting weights until what happened?
It
It
equaled
balanced
up.
up, right? Now, I happen to know, you know how much a nickel weighs?
No.
It's my lunch money. I know everything there is to know about that nickel, right? That nickel weighs 5 grams. So if I take it and I put it in there like that, what happened?
It's about equal.
It's about equal, right? It balanced up.
Yeah.
So what do you think that little purple thing over there weighs?
Weighs about the same
5
weight
grams.
as a nickel.
Weighs about the same weight, so it's 5 grams, right?
Yeah.
No. If I take a brown one and put it in there, what happened now? I still got my nickel. My lunch money's still over here, right?
Yeah.
Don't laugh. That's all I get. Okay? So, but it's unbalanced again, right? Because why?
Because you added more weight.
Because I added more weight over there, right? So if I take, we decided these things are about 5 grams, so I'm going to add another one over here, right? What happened to it now?
Now it's about equal.
I got 10 grams on both sides.
Yep.
Right, 10 grams of stuff, material. Now, what if I could very carefully carry this thing to the moon?
They'd probably
Set
float.
it down on the moon, and what's
This-
going to happen?
This is fly up right here.
It's going to fly up? No, it's not going to fly up. Because I'm not going to put any force to it. I'm going to very carefully carry it, and the only way it's going to fly up is if I put force to it, right? Because it's just like this book, right? It's not going to move unless I put some force to it. Okay? So, what do you think is going to happen if I take that and carry it to the moon?
They're gonna be exactly equal.
It's not going to be exactly equal?
It would be,
It will be?
right?
Yeah. Why?
Because there's gravity and mass.
It has gravity and mass. Okay. But the gravity on the moon is only 1/6 of what it is here on the Earth. This thing doesn't measure the same. If I take this one to the moon, right? It's only gonna read 1/6, and you're telling me now that it's still gonna stay balanced when I go to the moon with that. You're right. But why?
All because the moon, you said, has gravity, right? Because it has material. So
Right.
it's gonna stay balanced.
Because whatever gravity I have pulling down on this side, this 10 grams here is going to pull down on that side with 10 grams force.
It's gonna be equal.
It's going to be equal, right? So it's going to stay balanced. That scale there, right, for measuring masses, right, is the same as this one. You've seen this one before, right?
Yeah.
Right, this is what is called a triple beam balance. And what it is basically the same thing. If you look down underneath here, there's a little focal point right here, right? And what we're doing is, instead of adding weights to one side of it and keeping the arm lengths the same, we're moving weights back and forth and making the arm lengths on the beam scale change.
What is it called?
The
It's a
triple
beam, right? Because each one of these things is a beam,
has three of
right.
them.
and we have 3 of them, so it's triple beam, right? And it works the same way as this. So if I were to take this thing and weigh it, my tennis ball, which weighs 57.5 grams or so, right? Right, very carefully take it all up and carry it to the moon. What do you think it's going to weigh when I get to
It's
the moon?
gonna weigh probably less.
Why?
There's gravity pulling down on the tennis ball.
What happened to this one?
Stayed the same.
It stayed the same when I took it to the moon. So what do you think is going to happen to that one? That's the same kind of scale.
I think it's probably gonna stay the same.
Because what we have, right, is we have a pivot point here, right? Okay, and what we do is the ball is on one side, right? And then we're moving these back and forth on the other side to get the reading, right? What we're doing is balancing it up by moving these 3 little weights that we have up and down the beams, right? And when we do that, we have the gravity on the moon is pulling down on the 3 beams. It's also pulling down on this ball. And if we get it balanced up here on Earth, right, and make a reading, and we carry it very carefully to the moon, right, On Earth, our Earth's gravity is pulling here, it's pulling over here with equal forces, right? It keeps it balanced. I take it to the moon now, which is only 1/6 of the gravity, but the gravitational force pulling down here and the gravitational force pulling down over there are the same, so we're going to get the same reading. If you weigh 120 pounds, I take you to the moon and hang you on one of these spring scales, right? What are you going to weigh?
Not 123. Less than that, like 116.
No, you're going to weigh,
1/6
gravity
of
is 1/6, you weigh 120. 6 into 120 is what? 1/6 of 120?
It's like 60,
20 pounds.
20.
Yeah. 6 into 12 is 2,
Oh, yeah.
right? 20 pounds. So, if I take you to the moon, you weigh 120 pounds on Earth when I hang you off of here, right? I take you to the moon and I hang you off of there, you're only going to weigh 20 pounds. But if I take one of these scales, like it's in the doctor's office, it's the same kind of scale as this. It's a triple beam balance also, and I weigh you, right? You're going to weigh the same as far as the scale is concerned. Right, because why? Gravity, that 1/6 gravity is going to be pulling you down on one side of the scale, and it's going to be pulling down on the other side of the scale, and things are going to balance up the same point, and you're going to weigh the same. What about this one?
It's an electric scale.
It's an electric scale. Wonder what it does.
It measures weight.
It measures weight in grams and I think kilograms.
It measures the weight in grams, right? That's a little electric scale. And right now it's reading all kinds of things because I got it off balance, holding it up here. And we've got a little digital readout, right? So if it's down on a level surface, it should be reading 0.
Mm-hmm.
Right? Now, that electric scale weighs things pretty much the same way as this does, right? There's a little spring or fair or whatever you have in there, right? Which is when we put some weight on the platform here, right? It's going to stretch that, and the amount and the electronics in there measures how far it stretches. So if we were to take this now, and we were to go and weigh it, right? It reads
4 grams.
4 grams, right? We take it to the moon, where the gravity is 1/6, right? And it operates the same way as this spring scale. It's going to weigh 1/6 to 4, okay? 1/6 to 4 grams. All right.
How about that nickel? Didn't you say it weighs 5 grams?
It weighs 5 grams. This scale is off a little bit. The battery is probably, it only says 4, right? But the nickels weigh 5 grams, right? That's why I always carry a nickel. So if I have to weigh something, I can build me a scale. And I know I have a standard weight, which is a nice new shiny nickel. And
Probably
I
not
can
new,
buy my
but
lunch, right?
yeah,
Okay.
probably not new, but shiny.
Well, it's pretty new. It's not all wore out, so. Now, what have we done?
Measure things.
We measured things, and we've talked about
Throwing the
Baseball.
ball.
throwing a baseball, and that's the only thing we did, right?
Yep.
We could have become famous,
Oh yeah.
right? Because what we did, what we talked about,
We're gonna or we could have became?
we could have been, right?
Oh.
If we would have been a little bit smarter, right? We could have become very, very, very famous. We could have even been knighted, right?
Only 8th grade. Come on.
Hmm?
Only 8th
We
grade.
only to knight you.
Oh no. Do it to him, but it's all good.
Right. But what we just did was we went through all of Newton's laws of motion.
Isn't that guy that signed happened on an apple? Apple fell off
Well,
a tree?
that's the story, right? Sir Isaac Newton was a scientist and a mathematician, right? And the story is that, yeah, he was sitting underneath a tree out in the apple orchard, and the apple fell down and hit him on the head, right, or whatever, and he had
Blah.
he finally come up with this idea of gravity, right? Now, one of the things about Sir Isaac Newton was he wrote everything down, and he was a very good mathematician, so he could, calculate all these things. Probably, right? He did this in the 1700s or so forth. There was probably some guy long time before him was sitting underneath an apple tree, and an apple fell down and hit him on the head, and he says, I wonder why that happened, right? And he probably figured out gravity. But you know what the difference was between the two of them?
There was like no intelligence when that first dude found it.
Well, the first guy was probably just as smart as Newton.
Yeah, but like, he died.
Well, so did Newton.
But he couldn't write nothing
But
down.
we all know about Newton. Why do we know about Newton? We don't know about that other guy.
He couldn't write nothing down.
Hmm?
Couldn't write nothing down.
He didn't write anything down. Maybe he could, but he didn't. Right? He just sat back there and said, okay, yep. There
It's
you go.
all right.
The apple fell down, and because there's got to be some force that's pulling it down, right? And he may have come up with the same idea. Right? He just didn't write it down. He may have been just as smart as Newton, but he didn't write anything down. The reason we know about good old Sir Isaac is because he wrote a lot of stuff down, and he was pretty famous for some other things that he did.
You gotta be smart.
But his first law is every object remains at rest or moves at a constant speed in a straight line unless it's acted upon by an outside force. Okay? No big deal. All these things that we have sitting here are what? What are they doing?
Nothing.
They're doing nothing. They're at rest. They're resting.
Yeah.
All right?
It's true.
They are. They're at rest. Right? Because all the forces on them are balanced up. Right? At least as far as we're concerned right at the moment, they're at rest. Right? The gravity's pulling down on the book. The table's pushing up with an equal force. It's saying at rest. Right? There's nothing, no force moving, pushing it this way. Right? Causing it to move. Right? And to get it to move, what do I have to do?
Push it.
I have to put a force to it, right? Right, to get it to move. So that's Newton's first law. Now the second one is for an object to change motion, right? That motion has to have a force, right? And the motion that it changes to is in the same direction as the force. In other words, if I take this ball and I wind up and throw it in that direction, right, I get it to moving because I'm putting a force to it, and when I let go of it, the force is pointing off in that direction, so that's the direction the ball is going to go. If the force is off in this direction, which way is the ball going to go?
It's gonna hit me in the head
It's going to hit you in the head, right? And it's going to travel until what?
until it hits my head.
Hits the head, all right? And when it hits your head, what happens?
It's gonna fall
Why?
because of gravity, and there's no other force pushing it the other way.
Oh,
I'm just stopping
yeah. Well, how did you stop
it. It hit me.
it? It hit you, right? Right, and when it come up and it hit you in the head like this, right, I put a force to it, right? And if I'm out in outer space and it's going to be traveling along here like this at 100 miles an hour, right, and it hits me in the head,
It's gonna bounce all the way back.
it's going to stop,
Yeah.
right? Because my head's putting a force to it, right, which is going to slow it down and make it stop.
It'll probably bounce off, but it's just.
Well, that's another. If we were
Yeah.
both, my head was very, very hard and the ball was very, very hard, it would just go up and stop. Right?
Hard-headed.
Hard-headed, right?
It's like my phone.
And for every action, there is an equal and opposite reaction, right? Which was what we did here by
Okay.
spring scale, right? Gravity is doing what?
Pushing it down.
Pushing it down. The spring is doing what?
Pushing
Pushing
it
it
up.
up.
Pushing it up, and it's standing still.
Equal.
Equals
Or-
forces.
So equal forces, and they're in what? In opposite
Directions.
right? They're equal and in opposite directions. If they weren't equal, what's going to happen? If I had a little more force,
It'll be uneven.
yeah, it'd be uneven. And if I had a little, and if it was going up like this, right, there'd be more force pulling
Pulling
up
it up.
than there was pulling down. Right? And if I let go of it,
More force pulling it down.
more force pulling it down. Okay. So, what else we got here? Some terms that we were talking about: mass. Right, mass is the quantity. One of the definitions for mass, right, is the quantity of material. Right, your head has a certain mass, his head has a certain mass, and therefore your two heads have some gravity. This ball has a certain mass, a certain amount of material. This has a certain mass onto it, and there's a gravitational attraction between the two of them. There's also a gravitational, much stronger gravitational attraction between the ball and the Earth, so will let go and falls. If I take these two balls to the moon,
Probably attract to each other more than they would to the floor or to the ground.
well, they're going to attract each other the same amount as they do here, right? Because their masses
One's equal. Oh no.
stay the same,
Yeah.
right? If this has a certain mass on Earth, right, I take it to the moon, it's going to have the same mass. Right? The mass doesn't change. The two masses are the same. One word that we didn't use was inertia, right? What's inertia? Do you have any idea what inertia
When
is?
you're in a car and then you're going fast and you stop, you go front. The car stops, but you keep on going.
We
That's
talked
good.
about that last year.
That's good. Because that's exactly what it is, all right? And inertia, the inertia is the
Right.
tendency of this thing continue to go in the same direction, or if it's sitting still, right, it wants to stay still, right? And the amount of inertia is dependent upon the mass, right? Bigger the mass, the harder it is to get it to move, harder it is to get it to stop, right? Harder it is to make it turn. And that's exactly what happens when you're riding in a car, if you're going down the road, right, and they step on the accelerator pedal, right? Drive one of those big old Dodge Chargers that I used to drive, right? Boom. And what happens to you? When you accelerate,
You go
you
forward.
want to
back.
stay. You
Yeah,
want to
you
stay
go
still,
back.
so you go back, right? When I slam on the brakes,
You go forward.
you want to keep on moving at the same speed the car was going, so you're going to go forward. You go around a turn,
You're
You're
gonna
gonna
go
go
to the
that way.
side.
you're going to go one way or the other. Okay, that's inertia, right? No, the amount of energy that this thing has when we throw it is something called momentum, really, right? Which is how fast it's going times its mass, right? It's the mass of the object multiplied by its velocity or speed. You know the difference between velocity and speed?
Not really. I thought that was the same thing.
You thought it was the same thing?
Yeah.
Yep.
Well, in the scientific world, it's a little different. Speed is so many miles per hour,
How fast
say
it's
for
going.
instance, how fast it's going. Right? And it could be in any direction. Right? Velocity is be 50 miles an hour east.
At a certain.
It has a direction,
Yeah.
right? Velocity has a direction to it, right? Where speed doesn't. If you say, okay, it's going 55 miles an hour, yeah, we don't know what direction it's going in, right? It could be going up, down, round, back and forth, and whichever way. But when we say it's going 50 miles an hour east or 50 miles an hour north, 50 miles an hour south, then that's velocity. It has a direction. We know which way it's going. Right? Now, my ball. That's it's spring training, right?
Yeah.
And it has a certain amount of mass, right? And we said that that mass does not change, right? No matter where we are with it. The only problem is my hero, Albert Einstein.
What he wrote or he wrote?
Hero.
Your hero or he wrote?
Hero. I admire
Your
him very
idol.
much. Okay, yeah, I know. But I come up with a different idea of mass, right? Come up with a thing called the theory of relativity. And the theory of relativity says the faster this ball goes, the more
farther
mass
it's
it
gonna
has. Right? So if I were to take and I were to throw this ball at the speed of light, which is 186,000 miles per second, which is pretty fast. Pedro can't do that. Right? Then what happens is the mass of this ball becomes much
Heavy.
heavier, increased, right?
Yeah.
So that's one of the things in the theory of relativity is the mass changes a little bit, right? So to give you some idea is, and it's called inertial mass because it's because it's moving, right? And the formula, and it's theory relatively, and the formula for it is the mass moving is equal to the mass at rest divided by the square root of 1 minus the velocity of the mass, in other words, how fast it's traveling, divided by 186,000 miles per second, which is
Really fast.
really fast, right? This is speed of light. Now, normally, if we wouldn't worry about that, right? Because we don't have anything that's traveling anywhere close to the speed of light, right?
Except for light.
And so it really doesn't matter too much to us. But it is possible for this mass to change, right? Right, the number for the mass. As an example, a Boeing 747, right, weighs at takeoff 833,000 pounds, which is a lot. Okay? That's one of those big commercial airliners. And if we get that airplane up, it won't fly 1,000 miles an hour. But if we could get it up to 1,000 miles an hour, right, its mass would increase, right? But it would only increase 0.000000833 pounds, which is
That's not even that much.
that's nothing, all right? We don't have to worry about that at all.
Probably about the weight of my nail clipping
Oh.
right there.
Right? So we don't have to worry about that, right? Normal everyday circumstances, we don't have to worry about the mass changing with the velocity, right? We can assume that the mass stays constant, right? The only time that the scientists ever really worry about that is if they're doing some particle tests and so forth, where they got some very, very small particles, subatomic particles, right? In which they can get to going pretty close to the speed of light, and their masses are going to change quite a bit. So the speed of light is the theoretical limit that things can travel, right? At this ball, right, as it approaches the speed of light, the mass is going to increase so much that it's going to be harder and harder and harder to put more force to it to make it go faster. And when it gets to the speed of light, the mass will be infinite or beyond our calculations, right? And we're going to have that. So what we've done, basically, is we've talked about Newton's 3 laws. That's what we did today. Newton's 3 laws of motion, right? And the first one was every object remains at rest or moves at a constant speed in a straight line unless what?
Unless there's another force.
Unless there's another force applied to it, right? To make it change directions or change its speed, either speed up or slow down, go left, right, up or down, right? Change in motion of an object corresponds to the amount of force and the direction of the force. In other words, if my ball is traveling along like this, right, I put a force to it this way, it's going to go
That way.
that way, right? And how fast it goes that way is going to be dependent upon how much force I put to it. Okay? That's the second law. And the third law is for every action, there is an equal and opposite reaction. My book is sitting over here, right? Gravity is pulling it down, right? It's not moving, so there's got to be another force in the opposite direction pushing it up.
The table.
The table, right? The table is pushing it up. What's holding the table? Because gravity's pulling the table down.
The nails.
The floor. What's holding the floor up?
The ground.
The ground, right? Right. So all this weight that we have here, like you and I, right? Well, another interesting one, right? Is if I'm walking along like this, right? What's making me move that way?
Your feet.
My feet. The friction, right?
Yeah.
It's putting a force to make me move that way. What's happening to the earth?
Nothing is staying the same.
How do you know that? I got another force down there. I got equal and opposite forces, right? So if I'm moving forward like this, right? That force is pushing me that way. There's got to be an equal and opposite force pushing the earth the other way.
They're still spinning.
But it's not very much because the earth is, it's not going to make much effect on the earth because the earth is pretty massive, right? It's going to take a lot of force to get it going. A lot more than it takes me to move across. But if we all got up in the morning, got in our cars, got on our bicycles, and started walking, and we all went in the same direction.
What?
Right? And all those little forces that we had was push the Earth in the opposite direction. We could change how fast the Earth rotated. Believe that one? And I'll tell you another one. We'll save that one again for April Fools.
For real.
All right, so now, you want to do this ball thing again?
No,
Why not?
Takes too
I'll
long.
bet you
it's complicated.
it's not complicated. I mean, Pedro goes down there and he gets big bucks for throwing baseballs, right? So,
I
why
didn't
don't-
get paid.
I can take this baseball. Pedro can throw it at 100 mile an hour, right?
Yeah.
Right. I can take this ball. This is not a baseball, it's a softball. I can take this ball, and I can throw this ball so that it travels about 1,000 miles an hour.
Are you lying to yourself or are you just
But
making that
just
up?
by myself. Take here, stand right here on Earth, right? My big old arm,
Bionic arms.
and I can whip this ball out so that it travels 1,000 miles an hour.
You're on the moon, right?
Go right here on Earth, right here. You don't believe that?
Nah.
All right, come back the next time, and we're gonna prove to these guys that I can do that.
All right, I'll be the catcher.
You gotta be the catcher, all right? You can be the catcher.
We'll wear a face mask this time. You might hit me
That's
in the head.
Is it for today? We went through
How
Newton's three
speed
laws of
is,
motion.
You know the
and
thing
there's
that measures the
demonstrations that
speed?
Very. Yes. That demonstrated those three laws without even getting into all the details of it. And it's very, we did it with some very simple things like baseball, my spring scales, my balances, and what have you. That's it for today. See you the next time.